The sine and cosine functions. There's a total of 6 trig functions that we will eventually look at, and they correspond to the 6 trig ratios that we had looked at with the right triangle trigonometry. That would be, in addition to these two, that would be tangent, cotangent, secant, and cosecant. However, for the time being, what we're going to do is just focus on sine and cosine. See, these functions have a whole lot of information to be learned about them. There's tons of details in there, and if we can just focus our attention on these two functions right now, sine and cosine, then once we have a good grasp of that information, we can then take it and apply that information to the other trig functions. So if we really want to treat these as functions, what we got to do is get them into the coordinate plane. That would be the xy coordinate system. Okay, so what I have over here is a picture of a circle that is centered at the origin of our coordinate system. This would be the x-axis, and that would be the y-axis. Now, you may or may not remember, this is the equation of a circle that is centered at the origin. It says x squared plus y squared is equal to r squared, where r is the radius. It does appear to look like Pythagorean Theorem, and that is true. The equation for a circle is based off of Pythagorean Theorem, and we're gonna sort of see that in a moment here anyway. All right, so we got this circle. It's on the coordinate plane. We're going to identify a point and just call it P, and it could literally be anywhere on here, but for conveniency, what we'll do is just go ahead and put it into quadrant 1. Okay, so there's a point out there called P, and that point P has coordinates that go with it. It has an x coordinate and also has a y coordinate. Okay, and that means that to get to that point, you'd have to go to the right x amount, whatever that is, and then you're going to go up to the y value. So what I'm going to do is I'm going to highlight those components that would get us there. Okay, so here, that would be a distance of x, so whatever that number is, it's a distance of x out that direction, and then you're going to go up y units. That'll get you to point P. And then the radius, I'm going to go ahead and add that into there too, because we can. The radius is going to be the distance from the center of the circle, which is at the origin, out to that point P. Okay, so now this might actually make a little bit more sense about why the equation looks like Pythagorean Theorem. Because when you draw those components, you just end up with a right triangle, and that's Pythagorean Theorem. You take the leg squared and add them together, that should equal the radius squared. Okay, so Pythagorean Theorem is there. In addition to that, remember that when we first started looking at trigonometry, we defined the sine, the cosine, the tangent, the rest of them based off of right triangles. Okay, we let an angle be called theta, and then with respect to theta, we talked about the opposite, the adjacent, the hypotenuse, and then we named them. All right, now if you look at this, it's not that different, right? The sine of theta is still equal to a ratio. The cosine of theta is still equal to a ratio. All right, now our theta though, our theta in the picture, if this right here, the positive x-axis would be the initial part of our angle, and then it rotates out until it gets to point P, that would make this angle right here theta. Okay, so let's think about how we know sine as a ratio. The sine is the opposite divided by the hypotenuse. Well, if you take a look at where theta is here, the side that's opposite of it is going to be the y value. Opposite is the y value, and then the hypotenuse would be the radius here. Okay, so what we've really done is we've taken the ratio that we know from right triangle trigonometry, and we've applied it to an angle that is centered at the origin and then rotating as it rotates around. All right, likewise, the cosine of theta would be the adjacent divided by the hypotenuse. In this picture, the x component here would be the adjacent. The hypotenuse, again, would be the radius, so we get x over r. Okay, so we're now able to take a step away from right triangle trigonometry and start thinking about it in the coordinate plane, and instead of describing things with opposites and adjacents, we can actually use y values, x values, and even the radius to those points. Example 1, if the terminal ray of an angle theta passes through -3, 2, find sine theta and cosine theta. All right, what I'm going to start with here is drawing a picture similar to what we had in the above part here. Okay, what that means is I need to need to draw some axes here. All right, now the picture's not gonna be that large, but it's gonna be good enough to get the concept across here. All right, so I got my axes, the X and the Y axes. And around that, I'm gonna make a circle. Let's not make it too big. All right, we're gonna make a circle. And on that circle, there's gonna be a point P. Okay, that point P is gonna be the coordinate that he gave us, which was at -3, 2. Okay, so -3, 2 means that you gotta go back 3 units and up 2 units. So you're gonna go a little bit further to the left than you're gonna go in an up direction. So I'm gonna put the dot about that location there. Okay, now it doesn't need to be perfect, it's just, 3 is bigger than 2, so I wanna be a little bit further out to the side there. And now that I got that point located, I'm gonna go ahead and draw that right triangle. There. So you're gonna notice that this is in quadrant 2 versus what we saw at the beginning part, which is in quadrant 1, but it's all gonna work out. All right, so our X component, that's gonna be the -3. The Y component, the vertical is gonna be a 2. So you got -3 and you've got 2. All right, the radius, we don't know at the moment. We don't know that one. Okay, and now do we really need to know it? Let's see, remember that the sine of theta, as we're gonna define it now in the coordinate system, is gonna be the Y value divided by the radius. Okay, so the Y value is the 2. We have that, we actually do need the radius. You need the radius so that you can complete this problem. By the way, we're not gonna be figuring out what theta is at all here. That's not the point of the question. The point of the question is that if you have an angle that rotates all the way out to this position, so that's theta. If you have an angle that rotates all the way to that position, what would the sine of that angle be equal to? And it's gonna be equal to the Y value divided by the radius. Okay, so now as a little bit of side work, we're gonna figure out what that radius is, and that's just using Pythagorean Theorem. We're gonna take 2 squared plus 3 squared. Notice I did not use -3 squared because -3 times -3 will become positive anyway. So it is important that in the diagram you know this as a -3. That's gonna pop up in a moment. But for the sake of figuring out what the hypotenuse or the radius would be here, you can just drop that negative because it'll become positive when you square it anyway. All right, so 2 squared is 4. 3 squared is 9. Together, that's gonna give you 13. All right, so the hypotenuse or the radius is not 13, but it is gonna be equal to the square root of 13. It's gonna be equal to the square root of 13. So we'll go ahead and add that to the picture. This is square root 13, and we're gonna leave it as a square root 13 and not worry about not doing decimals. It's just gonna make it messier if we actually do that. All right, so the sine of theta will be the Y value divided by the radius. That is going to be 2 over the square root of 13. Now, of course, we don't like having radicals in the denominator, so we're going to fix that up by multiplying the top and bottom by the square root of 13, which will give us 2 square root 13 over 13. All right, for the cosine of theta, we're going to have x over r. Good thing is we've already figured out what the r value is. Okay, so the x is going to be the -3, so that's where the negative becomes important here. You're going to get -3 over square root 13, which, once you have it all fixed up, will be -3 square root 13 over 13. So those are your answers. And again, we did not have to figure out what the angles were. It was more about understanding the new way that we can define the sine and cosine. Example 2. If theta is a 4th quadrant angle and the sine of theta is -5/13, find cosine theta. All right, so let's go ahead and start with a picture for this. It does talk about a 4th quadrant. Okay, so I'm gonna go ahead and draw the axes again. All right, there's axes, and I'm gonna go ahead and put the circle on there as well. Okay, so I'll center at the origin and choose some size for the circle. All right, again, the picture doesn't need to be perfect, but this will help to definitely organize things. All right, so this is quadrant 1, that's 2, that's 3, and that's 4. So we're hanging out over here. That's where theta is at. We don't know exactly what theta is. We don't know what the measurement of theta is. However, we are told that the sine of theta is negative 5/13. And what we need to remember here is that the sine of theta is equal to the y value divided by the r value. It's the y value and the r value. So the 5 is going to be the y value, okay? And the radius is going to be 13. So the distance from the origin out anywhere is 13. All right, now this is actually a negative 5/13. And we have to think about why that would be true. Okay, so in any of the quadrants, you've got x's and you've got y's, and those x's and those y's can be positive or negative. Like in the above one here, that x was a negative 3, but then you had a positive 2, so that's quadrant 2. In quadrant 4, your x's, let's write this out to the side here, your x's will be positives and your y values will be negative because you go out to the right and then you go down. So it's going to be a positive and negative. Okay, so now that negative is going to start to make sense here because if we attach it to the 5, if we attach that negative to the 5, that tells us that the y value is a negative 5. And that sort of confirms that we're in quadrant 4 because that would move you in a down direction here. Okay, so our point, I don't know if we can really estimate where it would be based off of just the y value and the r value. It's a little easier to do that when you have an x and a y. Yeah, so what I'll do is just put a point out there. Okay, now it may be closer to one side or the other, but we'll just put it in that spot. We'll go ahead and connect to the origin. That would be the radius, which is 13. And by the way, the radius is always going to be treated as a positive number. Okay, so your x's and your y's can be positive or negative, but the radius is always going to be treated as a positive. Okay, so you got a positive 13. This is going to be the negative 5. Okay, the negative 5, and then we don't have that one. However, you could do Pythagorean theorem to figure out what this is. Okay, and we are going to need it, so I'll go ahead and just take care of that right now. All right, so we've got 13 as the hypotenuse. So what we'll do is take 13 squared and subtract the 5 squared. So we're working backwards with Pythagorean theorem to get a leg length versus trying to get a hypotenuse. All right, so 13 squared is going to be 169. 5 squared is 25. And if you subtract those two, you're going to get 144. Now, this is also what we call a Pythagorean triple, so you may remember these numbers from different problems before. But when you subtract, you get 144, which the square root of 144 is actually 12. Okay, so my picture is really not to scale here. That'd be 12. It's actually going to be much closer to the x-axis because it should only be down 5 but out 12 units. But for the sake of getting everything organized, that'll be fine. All right, now we need to figure out what the cosine of theta is. All right, so technically the theta that we use to draw this would be taking us all the way around to that side. So this is a really large angle measurement of theta. However, when you're doing these types of problems, you are allowed to just think of theta as being the angle that would be sort of tucked inside of your triangle. Okay, now we're always going to build the triangles attached to the x-axis. That part's not really described yet. It'll show up in a different lesson. Okay, but we're always going to make these triangles attached to the x-axis. In that angle that we have sort of tucked between the x-axis and our radius, that one you can just treat as theta and it'll all work out perfectly fine. All right, so for cosine, what we're going to need to use is the x value divided by the radius. Okay, and then the x is what we just discovered using Pythagorean theorem. So the x is going to be 12. It is going to be a positive 12 because you got to go out to the right. So it's going to be 12 over 13. And that's what we're looking for our answer. For example number 3, we're going to create a couple of diagrams that are going to help us summarize the quadrants where we should expect sine or cosine to either be positive or negative. So if we go back to examples 1 and 2, let's take a look here at example 1. The theta that we had for that problem took us over to the second quadrant. And when you ended up in the second quadrant, the sine of that angle was a positive number. It ended up being a positive number, but the cosine ended up being negative. That was because the y value, which is part of sine, was a positive number, but for the cosine, the x value was a negative for that spot. All right, and then if you look at example 2, the theta that we had here took us all the way to the fourth quadrant. So in that case, the sine ended up being negative because your y value was a negative number. However, your cosine was a positive number because that was to the right. Okay, so depending on which quadrant you're in, you can get a positive or a negative for sine and cosine. Let this diagram be the sine, okay, and we'll let the other be cosine. All right, so for sine, that is the y value divided by the radius. Now, the radius is always a positive. It's the y value that we're going to look at to determine whether or not we'd have a positive or a negative. Okay, so in quadrant one, the y value is a positive because whenever you plot a point out here, you'd go to the right, which is your x part, but then you'd have to go up. You'd have to go up, which is a positive number. So sine's going to be positive in the first quadrant. It's also going to be positive in the second quadrant because that is also in an up direction, which is what the y direction is. Okay, now if you're in 3 and 4, that would be in a down direction, which would mean that you have negative y values, so these two quadrants would be negative. Cosine is going to be based on x over r. So the r is always positive, that has no bearings on any of this. Okay, but for x, we have to think about when is x positive and when is x negative. X is going to be positive if you go to the right, it's going to be negative if you go to the left. So these two quadrants, the first and the fourth, are going to be where cosine ends up being positive. Okay, and if you go to the left, those would be negative x values, so you get negative answers for that. All right, so what happens if we choose an angle measurement that isn't actually in a quadrant? What if we choose an angle measurement that is between quadrants, like at 90 degrees, or 180 degrees, or 270, or even 0, which same thing as 360. What if we choose one of those? What type of an answer do we get for that? Well, those answers are either going to be -1, 0, or 1. Those are the only choices that actually end up happening. And we can actually figure out why those are if we consider these descriptions. That sine would be y over r, that cosine would be x over r. We can easily figure that out. Okay, so let's take a look at this first one here, the sine of 90. Okay, so I'm going to look at this picture because that's sine. Don't look at cosine right now. The sine of 90 is going to be right here. The sine of 90 is going to be right here. All right, and in any of the other pictures that we did, we were able to draw right triangles. You were able to do that because you had an x and you had a y component. But if you're at 90 degrees, you actually don't have any x component. There is no left or right movement here. It's just strictly straight up at that point there. Okay, so there's no x. The x is a 0. All right, but the y value, this is really interesting here. The y value is actually the same length as the radius. Right? The y value up to 90 degrees here, at 90 degrees here, the y value at 90 degrees here is the same thing as the length of the radius. So if you take the same numbers and divide them, you end up getting back 1. Okay, so the sine of 90 is equal to 1. All right, so let's take a look at sine of pi. Okay, so pi is over here. It's the same place that 180 is at. Okay, and you're going to notice that line right there is sitting between the positive and the negative. There's a transition between positive and negative. All right, so which of these looks like the best choice? That would be a transition between positive and negative. 0. It should be 0. Okay, now why is that though? Let's think about it. If you have a point that's out here, you've got an x value that takes you in that direction, but your y value is 0. There is no y value here. You don't go up, you don't go down. So if the definition of sine is y divided by r, you're going to be dividing a 0 for the y value over your radius, which gives you back 0. All right, let's take a look at cosine now. We got cosine of negative pi. All right, being negative pi just means that you're rotating in a clockwise direction. Okay, so instead of rotating that way, you're actually just going to rotate here. It does end up getting you to the same place that positive pi would. Okay, so if you do negative pi, just takes you out to this location. We're here. All right, that is not sitting between a positive and a negative. So it's different than what was going on in sine. Over here, your x value is all you've got. There's no y value. It's going to be 0. Okay, so it's an x value. That would be negative taking you in this direction. And that value would also be equal to the radius at this spot, right? You have, it's a lot like what we saw here with the sine of 90 where the y value was the radius. Okay, the x value here is the radius, except that the x value is negative. So if we take a negative number and divide it by itself, you get back -1. So that's what that'll be equal to. All right, cosine of pi over 2. Pi over 2 is the same thing as 90 degrees. If this is pi, then half of a pi is going to be right here at 90 degrees. Okay, so at that spot, you sit between a positive and a negative. So if it's a lot like sine, you're going to get back 0. But we can definitely investigate it here. All right, so at pi over 2, at this location here, your x is actually going to be a 0. You don't have any left or right movement there. You're just strictly y value that takes you up. So if you divide 0 by your radius, you get back 0. All right, let's go ahead and type these into the calculator just to verify that these answers are correct. First, the sine of 90. Okay, so the sine of 90 does equal 1. So that one is correct. All right, next, actually the rest of these are all going to be in radians. Okay, so what we're going to do is switch our mode over, because if you type these in degrees, it's not going to show us these answers for sure. All right, so we're in radians. We're going to do the sine of pi. We'll do the sine of pi, and that comes back to be 0. All right, now if you do use the sine of 3.14, that is maybe not going to come back as 0. Might come back to really close. Let's see what that looks like. The sine of 3.14. All right, yeah, so you're going to see that that's really close to 0, but it's not actually 0. So if you have the option to use the sine, to use the pi symbol, definitely do that. All right, cosine negative pi. So the cosine of negative pi, that'll give us -1, so that checks out. And last, we're going to do the cosine of pi divided by 2 and see that we get 0.
Later, blah.